Welcome back, Wisdomers. Gradient descent is the essential foundation for anyone looking to master how machines truly learn from data. Now I recommend staying with us until the very end, as we'll be covering several high-value concepts that bridge the gap between theory and practice. By the end of this video, you will have a clear, intuitive understanding of the mechanics behind this powerful algorithm. Take a look at this function, y equals x minus 1 squared. Our objective is simple. Find the value of x that results in the lowest possible value for y. Now, to start the algorithm, let's pick a random starting point, x equals 5. At this position, y is far from its minimum. This confirms that we need a systematic way to descend to the min point. We refer to our initial guess of x equals 5 as x-old. To move from this starting point toward the global minimum, gradient descent utilizes a precise mathematical update rule. This computation allows us to iteratively refine our position. The fundamental equation for gradient descent is defined as x new equals x-old minus the product of the learning rate and the gradient of the function. We understand the generalized formula at the end of this video. Let's visualize exactly how gradient descent locates the minimum through a practical example. For this demonstration, we will set our learning rate, represented here by the symbol eta, to 0.1. Recall that the derivative of our function is 2 times x minus 1. If we evaluate this gradient at our starting position of x_old equals 5, we get a value of 8. Now we perform our first iteration by substituting these values into our formulae. Our new x value is calculated as 5 minus the product of our learning rate 0.1 and our gradient 8. This results in a new position of x equals 4.2. Visualize in graph x new equals 4.2 means after first iteration x moved 0.8 units towards minimum point 2. Before we move on to the second iteration, if you find our content helpful, please take a moment to share this video and subscribe to our channel. In addition, be sure to visit wisdomers.in for interactive quizzes and projects. Now we perform our second iteration. Our previous result, x equals 4.2, now becomes our new x-old. At this new position, we recalculate the gradient. 2 times 4.2 minus 1 yields a slope of 6.4. Using the consistent learning rate of 0.1, we update our value, x new equals 4.2 minus the product of 0.1 and 6.4. This results in a new position of x equals 3.56. As you can see, notice in the graph how we moved one step near to min point after second iteration. The algorithm continues this iterative process. Observe the trajectory on the graph as the x value progressively converges toward the function's minimum point. As we reach the lowest point, you may notice the x value oscillating slightly, much like the motion of a pendulum. This behavior indicates that we have successfully arrived at the minimum, and we can now terminate the iterations. Please maintain your focus, Wisdomers, as we are now exploring the critical mechanics that ensure this algorithm works universally. While this is a comprehensive deep dive, the insights gained here are essential for your practical expertise. Let us now visualize the scenario where our initial guess begins from a negative coordinate. Using an initial value of x equals -5, we apply the identical update formula. Observe how, regardless of the starting position, each iteration systematically guides toward the global minimum. Now that you have a solid grasp of the intuition behind gradient descent, let's break down the mathematical formula that powers the algorithm. To find the minimum point of a function, we use the following equation. X new equals x-old minus eta times slope. While this formula contains two main components, the slope and the learning rate theta, the logic of the entire algorithm is driven by the slope. Let's focus on why the slope is the most critical part of this equation. Let's examine how the formula behaves in a real-world scenario. Suppose we are at a point on the graph where x equals 5, and the calculated slope at this position is 8. Because the slope is positive, the function is currently ascending, or moving upward as x increases. To find the minimum point, the valley, we logically need to move in the opposite direction, backwards toward a smaller value of x. This is where the subtraction in our update rule becomes critical. Let's look at the equation again. X new equals x old minus the quantity eta times slope. When we plug in our positive slope, where x old equals 5 and slope equals 8, the formula becomes x new equals 5 minus the quantity eta times 8. By subtracting a positive value from our current position, the new x value will be less than 5. Mathematically, the formula recognizes that a positive slope means we have gone too far to the right. By subtracting the slope, the algorithm automatically pushes the x value to the left, effectively moving us down the curve and closer to the minimum point. Now let's examine how the gradient descent formula handles a point on the opposite side of the minimum. Suppose we are at a point on the graph where x equals -5. And the calculated slope at this position is -12. A negative slope indicates that the function is currently descending as x increases. In this part of the curve, the minimum point lies to the right of our current position. Therefore, to reach the bottom of the valley, we need to move in the positive direction, increasing our x value. Let's see how the gradient descent formula mathematically ensures we move in the right direction. X new equals x old minus the quantity I beta times slope. When we substitute our values, x old equals -5 and slope equals -12, the equation becomes x new equals -5 minus the quantity eta times -12. This is a critical moment in the algorithm's logic. In mathematics, subtracting a negative number results in addition. Consequently, the formula simplifies to x new equals -5 plus the quantity eta times 12. Because we are now adding a value to our starting point, the new x value will be greater than -5. By turning the subtraction of a negative slope into an addition, the formula automatically realizes that we are to the left of the minimum and pushes the x value to the right. It's a long video. Still, we need to cover learning rate. Stay focused, wisdomers. While the slope determines the direction of our step, the learning rate determines the size of that step. We understand with an example. Let's revisit our earlier example, where x old equals 5 and the slope equals 8. We will compare how the algorithm behaves with two different learning rates. Scenario 1. A small learning rate, where eta equals 0.1. Using the formula x new equals x old minus the quantity eta times slope. The calculation is x new equals 5 minus the quantity 0.1 times 8, which equals 4.2. With a learning rate of 0.1, the x value moves from 5 to 4.2. Take a look at the jump in the graph. A small jump. Scenario 2. A larger learning rate, where eta equals 0.2. Let's look at an increased rate x new equals 5 minus the quantity 0.2 times 8, which equals 3.4. By doubling the learning rate, our jump becomes significantly larger. In a single iteration, we have moved much further down the curve. Advantage with large learning rate: we can move down fast in less iterations. Disadvantages with large learning rate: if the learning rate is too large, observe at the bottom the jump going to other side. The algorithm begins to swing to and fro across the bottom of the curve, instead of converging toward the minimum. Remember this point, we solved this problem in neural networks. Thanks for your patience and have a great learning.